Jodrell Bank, home of the Lovell radio telescope, a marvel of engineering, now having its 50th anniversary, and it's done marvellous work, and still is. And, you know, I remember at the time when this was simply a grassy bank, and now we'll look at the telescope itself. People believe it simply couldn't be built. Well, thanks to Bernard Lovell, it was built, and here it is now. I'm proud to say I've been there many times, and I've been up on that catwalk, but Christian hasn't. He's there now. I didn't like it. I wonder how he's feeling.
We're here on the telescope structure. We're going up about 100 foot, so we've got a lift.
I reckon everyone who sees the telescope must want to climb inside it. And, as the telescope is parked for engineering, today I'm getting the chance to do just that. Dr. Ian Morrison is my guide. As we travel up, the smell of oil and the surrounding steel serve as reminders that parts of the telescope were recycled from World War II battleships.
So,
here we are.
Here we are, green towel, floors are green, and now out on the telescope structure.
Wow.
Here we are, lovely views of Cheshire.
Yeah, and of the telescope. You really understand how big it is from up here, don't you?
Absolutely. It really is spectacular, isn't it?
The massive dish dominates the Cheshire landscape, and it's still a breathtaking sight, even on its 50th birthday. The construction of the Lovell telescope was a fantastic feat of engineering. Bernard Lovell is here on the right, beside engineer and bridge builder Charles Husband. Using more than 3,000 tons of steel, together they built one of the 20th century's most iconic structures. This previously unseen footage of the construction of the telescope was recently discovered in a Jodrell Bank cupboard and shows what a daring engineering venture it was.
From the Earth. Then you'll go
Patrick and Sir Bernard Lovell have been lifelong friends, sharing a passion for cricket and music as well as astronomy. As I continue my climb up into the dish, a journey I know Patrick has made many times, down below the old friends are meeting to discuss those early days.
You know, looking around at this radio telescope now, I cast my mind back to those days long ago when we were lying on our backs, plotting meteor trails for the then Professor Bernard Lovell. And now, how wonderful it is to have him with me 50 years later. Bernard, great to have you. Do you often think about those early days?
I do indeed, yes. The weather always seemed to be good at night. I remember lying in a deck chair looking at the meteors.
I remember too.
Correlating with the echoes, radar echoes inside a trailer. Marvellous memories. Yes.
Do you ever think then, if we get to this stage in half a century?
No, not at all. And as far as the telescope was concerned, well, I proposed that and had the greatest difficulty in persuading astronomers that it would be only good for 15 years.
Well, 15 years.
And now we're at its 50th year.
30 years ago, the telescope went through a massive upgrade, partly because of metal fatigue, but also to keep it at the forefront of research. Right.
And we're now going to climb up into the space between the old surface and the new one that was completed.
So why did they replace the old surface?
Well, they needed to take away...
The main addition was a new, smoother dish. It sits on top of the old one, which is now showing its age.
And the support structure...
Stepping between the two dishes is an eerie experience. It feels rather like climbing up into an astronomical cathedral.
The original surface of the bowl dates to 57. And smoother, more precise than the original, so it actually works better too.
Well, let's head up and have a look at it. It's an amazing space.
Oh, it's actually quite wonderful, and the echoes really sound lovely.
Yes, you should have a concert up here.
It would be rather fun. I don't think anyone's tried it yet.
The last few steps to the top are trickier, but it's worth the effort. Oh, wow! Look at that. That's just incredible.
It's quite impressive, isn't it?
It's huge. I kind of expected to see the view, but you're right in the middle of the dish. This is it, the Lovell telescope at Jodrell Bank, and we're right inside it.
Absolutely. If it's a sunny day, you really need sunglasses. It's so bright here.
And it's huge, the third largest steerable telescope in the world,
amazingly,
radio telescope in the
still
world.
after 50 odd years. That's
How big is it?
Well, 76 metres or 250 foot.
Big.
Big,
Anyway.
It is big, absolutely. We're standing, in fact, on a surface that was replaced just a few years ago. It's a beautifully smooth galvanised steel with a very lovely paint job. So the telescope is now smoother than it ever was. It's working better than at any time in its history.
So the radio waves come in from the cosmos, hit this wonderful dish.
And they're reflected back up to the focus, which is just below the focus box up there. A feed collects those radio waves, passes them into a receiver, which we cool to about 10 degrees above absolute zero, minus 260 odd degrees, and that makes them incredibly sensitive. So we can pick up incredibly weak signals.
Even at Jodrell Bank, today's radio astronomers have to contend with pollution from mobile phones and microwaves. It was a different story 60 years ago, where the then Professor Bernard Lovell began his astronomical research. During the war, he had discovered that even primitive radar equipment could detect meteors as they enter the Earth's atmosphere. His aim was to develop this new science, using it to explore the universe. Lovell's colleagues recommended the botanical site at Jodrell Bank, far away from the annoying Manchester trams and ideal for his pioneering radio research. The telescope can observe even in bad weather, but the rain has driven Patrick and Bernard inside, where they're looking over old footage and remembering how it all started.
There was so much electrical interference in Manchester that I sought permission to come to this place, Jodrell Bank, where I had been informed that the university owned a few acres of land for botanical purposes. And I was given permission to come here for 2 weeks and arrived in the middle of December 1945. And that's, for other reasons, my presence here was completely forgotten until Blackett wondered where I was in the summer of 1946, when in fact we had already been getting some interesting astronomical results. First of all, on the radio outbursts from the sun, and then on the reflections from what turned out to be meteor trails.
Yes, I remember that very well.
Yeah. And so the 2 weeks for which I was given permission is now extended for, I can't count the number of years, for 60 odd years.
The first large telescope on the site was the 218-foot ground-based dish, but it could only look straight up. It did do important work though, detecting radio signals from beyond our own galaxy for the first time. The new science of radio astronomy was producing exciting results, and Lovell soon realised a steerable radio dish would open up the skies still further, detecting faint radio signals from the distant universe. Work on the giant telescope began in 1952.
It took a whole year to complete the foundations, and we were then left, after enormous expense, with a massive ring of concrete on which was to be rolled hundreds of tons of steel.
How long did the Lovell telescope take to build altogether?
About 5 years.
Well, certainly we see here some of the early days, the early attempts at setting up the equipment.
Yeah.
And then, of course, you had more problems.
I think the trouble was that, in fact, I'd only realised quite recently that I was asking for something which was at the very limits of what it was possible to do with the technology that existed in those days. And the original design, which I wanted, was for an instrument which would work at relatively long wavelengths. And therefore, the original design had an open mesh as a reflector. And then, first of all, there was a very important discovery in radio astronomy, which that was the discovery of the hydrogen line emission on 21 centimeters. And so I arranged for the central region of the bow to be covered with a small mesh. And then later on, much more seriously, I was persuaded by the scientific advisor to the Air Ministry to make the telescope more suitable for the eventuality of having to deal with ballistic missiles.
Yes.
And then there was a further incident in 1956. We learned about the Tacoma Bridge disaster in Washington State.
Just collapsed, didn't it?
Just collapsed. Yeah. And we had tested the design of the telescope to wind speeds of 80. Then Husband, the consulting engineer, constructed a 10th scale model, and we put it in the wind tunnel at the National Physical Laboratory. And at quite high wind speeds of 60 or 70 mph, the telescope behaved perfectly. The racks and pinions, which had been taken from the dismantled battleships and rotated the elevation structure, behaved perfectly. And then the wind speed was reduced to about 30 mph, but fluctuations were put in. And then disaster occurred.
Yes.
The instruments were put in to simulate the racks and pinions were absolutely shattered.
Just the way they found up. We can see all the early materials here.
That is why we then had to put in the big wheel underneath it. At present, you can see a big wheel there. The present wheel is load bearing.
Yes,
but originally, it was an enormous wheel, which, as the telescope bow was tilted, moved on pneumatic wheels, pneumatic tractor wheels, in fact, and this took out any oscillations. So the telescope survived.
These dilapidated old sheds are the original Jodrell Bank observatories, and this is the original Jodrell Bank itself. It's here that Bernard and Patrick would have carried out their first meteor observations, and it was also here that the experiments in radar began, bouncing signals off the trails left by those same meteors. They quickly moved on from radar to radio, collecting signals from space rather than transmitting them. By tuning into radio waves instead of just relying on visible light, we can gather much more information. In this optical image of Andromeda, our nearest large galaxy, the light you see comes from the hot stars. In radio, we don't see the stars, but instead the cool gas which surrounds them. So why radio astronomy? Why are we looking in the radio at all?
I think a good example of how to think about that is a day like today, where you look up during the day now, you see sort of blue skies, clouds and so on. If we had radio sensitifiers, if our eyes were worked at radio wavelengths, you'd see a completely different view of the sky. Basically, you'd see straight through the clouds, which is lucky for us situated here in cloudy Britain. But you wouldn't have a bright sky. You'd basically be seeing straight out into space even during the day. And you see a completely different view of the universe. So sort of arching above us would be the Milky Way. You'd see very bright radio emission from the Milky Way. It wouldn't be light from stars, in fact. Stars are very faint at radio wavelengths. It's actually the stuff between the stars. So you actually get to see the electrons spiraling around the magnetic field of the galaxy, and that shines very brightly across the sky.
So you see our galaxy, but you see other things as well.
You do, yeah. I mean, sort of scattered across it are what look like stars. And in fact, when they were first discovered, people called them radio stars. When people first started doing radio astronomy back in the 1930s, and then, of course, Jodrell started in just after the war in the 1940s, you were seeing these bright things that looked like stars. They called them radio stars. It turns out that they're not stars at all. They're actually distant galaxies, the quasars, these sort of quasi-stellar objects. Again, they take the place of the stars in the radio sky.
So we now know these quasars are distant, but what are they?
Well, they're actually the cores of distant galaxies shining very brightly, and we think at the cores of those galaxies we have supermassive black holes, and as material falls in towards that black hole, it basically gets energy from the gravitational potential energy of the black hole. It heats up and it shines very brightly, so they sort of shine out like beacons sort of across the universe. Occasionally what we see are jets from these things, so we see these sort of often a double jet where you've got material that's sort of spewed out in opposite directions, well outside the sort of bounds of the original galaxy that the black hole is contained within. So those things have been, as you say, have been a major area of research at Jodrell ever since the early work in the 60s.
What are the other highlights of the telescope's 50 years?
Well, one of the big things that was done in the 1970s was the identification of gravitational lenses. And these things are these sort of classic examples of Einstein's general theory of relativity in practice, which is where you get light bent around a massive object. So when you have perhaps one of these distant quasars, it's way off in the distance, and between us and it there's another foreground galaxy. The light from that distant quasar can be bent around, and you can get a sort of distorted image of it, or even multiple images. A bit like looking through if you ever look through your bathroom window or something, it's all sort of rippled glass. You look out at something in the back garden, you can see multiple images of it, or sort of stretched out things. It's exactly the same sort of idea. So the first one of these to be discovered is something called the double quasar, where there were basically two quasars, two bright star-like objects that were first identified in a radio survey with this telescope. And then finally in 1979, when optical spectra were taken of these two images, it was realised that they were identical and that they were actually the same object.
And the last major area that we haven't talked about is, of course, pulsars.
Yeah, well, pulsars, of course, were discovered 40 years ago this year, in 1967, in Cambridge by Jocelyn Bell. And that result was announced, that discovery was announced in Nature. And then the week after that paper appeared, there was a paper from Jodrell Bank with its own observations of that first pulsar. And ever since then, that's actually been a major area of research here at Jodrell. So of course what these things are, they're the remnants of giant supernova explosions. So when a massive star at the end of its life explodes, the central part of the star collapses in on itself and it forms this incredibly dense object. It's basically a dead star, weighs about as much as the sun, but about the size of a city. So like Greater Manchester, maybe 20 kilometres across. And of course, as this thing collapses in, because it's conserving angular momentum, just like an ice skater when they bring their arms in, when they're spinning, they spin faster. So this star spins faster, and they end up spinning at maybe something like once a second or so. And it turns out that they radiate. Although these things are tiny, we can actually see them across the galaxy because they're actually shining by radiating radio waves principally, but also other wavelengths from the magnetic north and south poles. So if you can imagine a sort of effect where you've got two beams of light sort of shooting out from the magnetic north and south pole, then as the star spins, you get this sort of cosmic lighthouse effect where the beam sweeps past, and as it flashes past your line of sight, you see this pulse from the star, hence the term pulsar.
And some of these are rotating extremely quickly.
Some of them are, yeah. I mean, generally what would happen is when the pulsar is born, over the time following its birth, it slows down. So it gradually slows down as it loses energy. But occasionally you get pulsars in binary star systems, so they're orbiting another star. And if material can be passed onto the pulsar, onto this so-called neutron star, we call them, from the other star, then actually that transfers this angular momentum onto it and the star spins up, the pulsar spins up.
So it actually gets faster?
It actually gets faster, and you can end up with one spinning, we call them millisecond pulsars, that are spinning maybe with periods of, a few hundred milliseconds or so. So in fact, if you could listen to those things, you'd hear this incredibly high-pitched tone.
Normally though, they're slowing down, but occasionally you get these glitches. They're not just a steady decay.
You do, yeah, and in fact the telescope that's behind your shoulder at the moment is the 42-foot telescope here at Jodrell Bank. It spends its life, it has done for about 30 years, monitoring pulsars. So in fact it sits there, and basically when the Crab pulsar's up, the pulsar that's at the centre of the Crab Nebula, it basically follows that across the sky, tracks it, and what it's doing is it's measuring the rotation speed of the neutron star.
This is the sound of the pulsar at the heart of the Crab Nebula, all that's left of a star which went supernova in the year 1054. But these cosmic clocks tick at different rates. Have a listen to the pulsar BO329 in Perseus. Or what about the one in the Vela supernova remnant? Some are rotating extremely quickly. This one, B1937, sounds rather like an angry mosquito. Jodrell have been listening to pulsars ever since they were discovered, and in 2003 they found something unusual, the first double pulsar.
Well, the double pulsar is unique in the sense that we have two clocks measuring sort of space-time as they move through this curved space-time caused by the gravitational field of the companion. And so we see a number of different relativistic effects which have been predicted by Einstein's theory and all working here together in one system. So for instance, we can see that space-time is curved because once one pulsar is behind the other, the pulse has to pass the surface of this very compact object. Space-time is curved near this object, and so it has an extra little path length, which causes an extra delay in the arrival time.
So you see a change in the difference between the clocks?
That's right, and so that we measure that to about 100 microseconds. We also see that this system is emitting gravitational waves. Again, another prediction of Einstein, and so because we have masses moving around each other, they're emitting gravitational waves, and so that means that the system is losing energy. And this loss of energy causes the neutron stars to become closer and closer, and we have measured that to about 7 millimeter a day.
How did you discover a double pulsar in the first place?
That was actually, well, partly luck, partly systematic search. What we usually do, we scan the sky for unknown pulsating sources. And there are some certain characteristics of a pulsar, and we look out for them, mostly the periodic nature of the pulsars because the rotation period is so stable. And so in this case we found the fast rotating pulsar, which has a period of only 22 milliseconds first, and then it took us some time to realize that there was actually a second pulsation in the data which moved all around the other pulsar with the right orbital period. And so That's how we discovered that particular one.
It's slightly surprising that 40 years after the first one was discovered that you can still find new pulsars. Why haven't they all been snatched up by somebody already?
Well, first of all, our instrumentation gets better and better. The telescope becomes more sensitive. For instance, the Lovell telescope is more sensitive than it was ever when it was built before. And we observe wider bandwidth. So even though we have to live with some RFI caused by mobile phones and so on, we're able to observe with wider frequency ranges. And we get better. I mean, sensitivity, bandwidth, and experience, all that adds together to find more pulsars. With current technology, we know 2,000. In total, we expect that we have about 100,000 active pulsars in the galaxy. Among those, we expect actually to find sort of the last jewel that we're missing, which is a pulsar around a black hole. So that's our...
That's the holy grail.
That's the holy grail. That's right.
This animation made by Michael's team shows the predicted distribution of pulsars in our galaxy, the Milky Way. If you had radio ears, the drone would be deafening. As the radio astronomers of today look at distant quasars billions of light years away, it's strange to think that some of the first objects detected here at Jodrell Bank were very close by and man-made. By 1957, the telescope was nearing completion, but the cost of construction had soared to nearly £1 million. The cash had run out. With the telescope still to be finished and a government inquiry hanging over him, Bernard was almost at his wit's end. But then, a lifeline was thrown.
Along came Sputnik 1.
Yes. On October the 4th, 1957,
Yes.
when Sputnik was launched, was not a very happy day for us at Jodrell. We were in extremely serious debt. I think we were short of about $250,000. And the telescope was not finished. The contractors had gone on strike because there was no money to pay them. And I had said to a colleague, we need a miracle to save us.
And it happened.
And it happened in the case of Sputnik. Now, of course, Sputnik itself was transmitting, and that was a simple matter to detect that with a fairly ordinary radio receiver.
I heard it myself, yes.
And I had no intention of doing anything about it until I had a telephone call from Bob Coburn, whom I had known during the war. And his message was that there was no instrument in the country that could detect the rocket which launched Sputnik. And of course, the rocket was the world's first intercontinental ballistic missile. And he's asked me if we could try to do something. So we connected one of our meteor transmitters to the telescope, and within a few days we had the thrill of seeing what no man had yet seen. The radar echo from an enormous ballistic missile, which was then moving over Cumbria at a rate of about 17,000 miles an hour. Fortunately carrying a delicate scientific instrument, not a bomb, yes.
As the only large movable radio telescope in the West, Jodrell Bank was used by both Americans and Russians to track their probes. The Lovell telescope followed the probe Luna 3 in 1959 and received the first images of the far side of the moon. Then, in 1966, Luna 9 sent back the first images from the moon's surface, and once again Jodrell was asked by the Russians to provide independent confirmation of their triumph. But the telescope wasn't built for such earthly concerns, but for exploring the distant universe. By working with other telescopes, it can be made still more powerful. The Lovell isn't the only telescope on site. This is the Mark II, which does its own research but also works in concert with its larger neighbour. This image shows jets from the galaxy Cygnus A, as seen by two telescopes 5 kilometres apart. Combining signals from telescopes across the globe improves the resolution by 1,600 times, allowing us to see fine details in the centre of the galaxy for the first time. Merlin is a network of 7 telescopes centred on Jodrell. Professor Phil Diamond is in charge.
As well as controlling the Lovell telescope, It's actually also the control center for the Merlin array. And as you can see here, the controller is able to monitor what's happening at some of the outstations.
The telescopes currently communicate via microwave links, but from next year, the eMerlin system will use newly laid fibre optic cables to greatly increase the available bandwidth.
Once eMerlin is up and running, there will be a really intense science program. In fact, the day we switch eMerlin on, if we point at a patch of sky, we would have an image that is significantly better than that obtained by Merlin in the last 20 years if it was looking at that same patch of sky.
So you do 20 years worth of observations almost instantly?
Almost in a day, yes.
There are now plans for a massive radio observatory. The square-kilometre array will be built far away from radio pollution. The ultimate solution to that problem will be to put a radio observatory on the far side of the moon. These astronomical aspirations seem a long way away from those early, pioneering days of Sir Bernard Lovell and the telescope he built, which was only meant to last 15 years.
Looking at the old pictures here of the very early days, constructed moving ground, elementary equipment, and then from there arose this great telescope.
Yeah.
It's done marvellous work, and although it's no longer the largest radio telescope in the world, it's still in the forefront of research.
Indeed, we still think it's the best.
I'm sure it is too.
The telescope now is far, far better than it was in 1957. It has had two quite substantial modifications, and the telescope, which was originally designed to work down only to a wavelength of about a meter, is now an excellent instrument at 5 gigahertz, which is about 5 centimeters wavelength. So it is a much superior instrument to the one that was originally built.
We've seen these old pictures of the telescope being built with the early days of Jodrell Bank. We see the telescope as it is now,
Well,
and I've no doubt will go into the future.
Look, this telescope at Jodrell Bank, although it's working marvellously at the moment, obviously has a limited life. I think its life will not be limited by the structure, but by its ability to cope with the new demands in astronomy. I thought 20 years ago that, for example, we knew all that we wanted to know about the structure and evolution of the universe, and now we know almost nothing.
Bernard, thank you very much indeed. And once again, congratulations from the whole world.
There will undoubtedly be many more discoveries from the Lovell telescope in the decade to come, but its place in history, and that of the man whose vision made it possible, is already secure.
I remember Jodrell Bank when it was simply a grassy bank. And look now, home of still the most famous radio telescope in the entire world. It's been a great honour to be here on that telescope's 50th anniversary. So from a very rainy Jodrell Bank, good night.